in places because of that, but at least it's there. Okay, what happened to my sheet of paper as I was wandering around? There we go. So this is the introduction of Le Chatelier's principle. I'm going to look at the ceiling. Pour about 100 mils into each one of these. It is the equilibrium that you should be able to see on the board and is also in your notes. We've got CuSO4, which is blue, and CuBr2, which is green, as you probably know from looking at the Parliament buildings. This compound likes to change between blue and green. About 100 there. Okay. Can we see the colors? Kind of. Kind of. Or I could project it right at your faces. Ah, that's probably a little better. Excellent. Grab the lights.
Turn off all of them. So the back people.
Okay. We've got. I need something to weigh that into.
It's not very easy. That's not right. Dude, I can't even go outside with my hoodie on. I'm so cold.
There's a way, gentlemen. Okay, for the first one, we're going to take ammonium sulfate. Gentlemen, ammonium sulfate, I'm going to take about 50 grams. Ammonium sulfate will shift it which way? Will it become more blue or more green?
More green.
Why more green?
Because it will be a bit more acidic.
Because it'll be a bit more what?
Acidic.
Why?
Because it'll be ammonia.
It will be, I mean it will, but do we see H plus anywhere in the solution?
No.
So we're looking in ammonium sulfate. Here, grab a pen. NH4. Terrible pen. Throw that away. How's this one? Better. NH4, SO4, ammonium sulfate. Now, you drop that into solution, what's it going to do? In the process of dissolving, what are you going to get out of that? Not a trick question. There's only two things you can get out.
SO4.
SO4, so we're going to get sulfate, and we're going to get ammonium. And we'll get them in a 2-to-1 ratio. So when I drop this into solution, we're going to get ammonium and sulfate. So do we see ammonium anywhere in here? No. But we do see sulfate. What happens to the rate if you increase the concentration? It increases. Which way will it shift if we increase the rate by increasing the sulfate? Which way will it start going? Forward or reverse?
Reverse.
Reverse. We increase this concentration, that will increase the reverse rate, and then that will have to make up for it, and eventually the rates will become equal again. but it's going to shift that way because whatever, and this is the introduction to Le Chatelier's principle. Le Chatelier's principle is whatever you do, nature tries to undo. And so we're going to add sulfate, so it's going to take that sulfate away. And that's because of rate. We increase the concentration, we increase the rate of the reverse reaction, which means it's going to shove it over there. We'll see if it's true. So ammonium sulfate, add 50 grams. I hope I have the right one. Hold it, are these already pre-weighed? It turns out to be exactly 50 grams. I just wasted a lot of time. Yeah, that's exactly 50 grams. So we would expect that to go even bluer. Put that there to remind us which one's which. Now we also have ammonium bromide. What will ammonium bromide release? Ammonium and bromide. If we increase the bromide, which way is it going to shift?
Forward.
Forward. So if we increase the bromide, that means the touch nature is sometimes confusing. There we go. So now the bromide and the sulfate themselves are colorless, so they shouldn't be doing it. So let's add all of that to the solution, which is I just brought out here. Since the other one was pre-weighed out, I'm not going to worry about this one. I'm going to assume it is. And so what color should this one become? Green. Now for that one you can see it, because it's actually dissolving a little better. For the one that's dark you can't quite, but maybe I'll get you to come up. Let's try and get this all dissolved. Come on. So we have our original in the middle. We have our equilibrium shift in which it is shifted to the products over here. And we shifted it to the products by essentially just adding more reactant. Increases that rate, goes over there. If we add more product, SO4, it shifts it back to the reactants, which is this one over here. I wouldn't say it's a darker blue, but it's definitely a lighter blue. You can't see it up there, so come on up. File by, once I just make this a little safer so that you're not knocking this over. Nope, get up, stretch your legs. Look, come look, bask in the glory. Bask. Green,
Get up.
regular. Nope, you must bask. Different blue. Once you've seen it, you bask in the glory, go, let someone else go, but you must bask.
That's a different blue.
That's a different blue. Yes, different blue.
It's dissolved properly.
Pardon? It's not all dissolving. Maybe I read it wrong. I was supposed to add 50, but 5.
Oh.
So who knows? But it definitely shifted the equilibrium. It's a much lighter blue.
Maybe you should add 5 to the 1.
Now the question then becomes, bask, bask.
Well, they all except for the Mountain Dew.
I'm gonna add it to this one. This is the NH4BR again. Just because so we can get 2 green ones. Okay, we have our 2 green solutions. They're copper bromide. They've shifted over here. We added a lot of bromide. If I was to add more, do I have everyone?
Yeah.
If I was to add more ammonium sulfate to one of the green solutions, what should happen?
It turned green.
Go back to blue. So I'll take one of these. We can see we've now got 2 green solutions. And I'll put it into here. So that we can compare it with the original green. Did it go back to a blue? No? Then I must demand you come up here and look at it again. Because it is clearly not the same green.
It's white.
Is it this green?
It's
It's not white. No, come here. Come here.
It's
You
like a
say
very
this is
light
white.
blue.
Come on back.
It's a very
Come on back.
Everyone?
Everyone,
Okay, I'm basking. Yeah, now it is blue.
come. Is that not, I mean, it's got a lot more powder in it, but is that not blue?
That is
Yeah, that is blue.
It's turquoise.
Yeah, it's
Not
not,
even
it's not
like
green.
Space.
It's not green.
It's like an off
It's like
blue.
it's like a salty coral.
A coral. A coral.
Like
I
an
actually,
aqua,
I have no
aqua,
idea
aqua.
what it's called.
Coral is pink.
Aqua.
Very nice.
Pardon?
Coral is pink.
Yeah, but that is blue, is it not? Okay, everyone else who hasn't come up, come up. What are you doing?
Look at see.
No, come. Come. Look. Look at it. If it looks white from there, I want you to see it. Blue, green, went back.
Oh,
Blue,
so cool.
green, went back.
That's riveting.
Huh? Isn't it riveting?
Wait, what? Sorry.
So, this one was green, just like that one. I added more of the sulfate, ammonium sulfate, so it went back to blue. Now, it's not the same as that blue, it's probably not as far, but it's pretty close. Pardon?
That would kind of used to look like that.
Oh, probably if I stir it. I think there's a lot more powder in there that's not dissolving as well.
Is it gonna become like saturated?
I think it
Like
is
if you
saturated
kept
because it's
adding?
not dissolving, yeah. Okay, now. Woo. Darkness reigns. Now as I clean up this particular mess, get out your Hebdens, you can work on PLOD until I get set back up again.
I don't know why all these people do this. Come on. I felt the roof, bro. I'm sorry,
You were right.
You will get a quiz on PLOD. It'll probably appear in the Google Classroom. The other class is about a day behind, so once they're done, we'll pick the quiz date for both classes. So, pay attention to your emails.
Wait, negative 10 or 6? What's the bigger number?
What?
What's the bigger number? Negative 10 or 6?
Yeah. What was your thought?
That's wrong. That's wrong. Yo, take up the number. Oh, okay. I know, but what's the numbers that we have? That's all I'm saying, pull out that page. For E, for D? Yeah, we don't know if it's D, E, or F.
What?
We don't know which ones are D, E, and F. Yeah.
Oh, you just start working until you reach stuff you don't understand.
Oh, that. Oh,
Do that
okay.
for now. I'll put that on.
Okay, five,
I
six,
did it for
seven.
the previous unit. I used to not do it at all. But I'll go ahead and check. Well, hold it. I could probably figure that out right now. Hold it. Take this. We just started Le Chatelier's principle.
Yeah. Something like that.
So, when does Le Chatelier's principle start here? Equilibrium. So it goes up to page 49 is D.
Okay, right.
Okay.
Thanks.
So up to 40.
Page 50, Le Chatelier's principle.
Wait, no, how do we fill out E?
What?
Do we fill out E? Or are we just doing that?
We're doing that there.
Oh, okay, so we're not. Why'd you say that? No, I'm listening. Yeah, we should go.
Yo, answer this. Answer this. Why will this reaction not produce COCl2? This reaction. It will not produce this. It will produce this. Why? And then if the chemist can somehow obtain but number one, why will this reaction, that one's producing. That one, especially we didn't do it.
Exactly. Anyone have extra hydrogen?
Well, I think it's like extra hydrogen looks like
Potential energy is high.
Yeah.
Does that mean it has a lower energy overall system?
it's because this has two molecules and this has two molecules.
So
This is
overall
polyphenols gases. So it goes to this way because there's more disorder here than here. You know what I'm saying?
Whichever
Down
goes
there,
shorter,
there's
it's
high
high.
disorder. There's two
Yeah.
molecules.
That's what I'm saying, which side is high, which side's low.
That's why I won't produce this. But if the chemist could somehow obtain a pure, I don't know. Say that.
You guys, I cannot find extra hydrogen.
Yo, low-key, I feel like we didn't understand it. I feel like we didn't learn this.
So does that fall?
What did you not learn?
The pure, why would it, like, about the pureness of COCl2? Like, I understand, like,
Oh,
because
yeah.
of, like, because there's two molecules on the left and there's one molecule on the right,
Yeah.
or on the product, so
Yeah.
it'll always go to COCl2.
Yeah.
But I don't know why, I'm guessing there wouldn't be pure COCl2, right?
Yeah.
I don't think it'll remain pure, I don't know why.
Oh, whoa, what does that mean?
That it's an equilibrium,
Right. So as soon as you have some of that, what happens?
it would turn to the,
Yeah. And not all of it, but it won't be pure. So this, you learned it, but you just learned it because you learned what an equilibrium was. I never gave you it's your understanding of, do you know
It's
that
fine, it's
equilibriums
fine.
always
Yeah.
go? So even if you got a pure sample of that, like those two together, it will never stay pure, because as soon as you do that, it's gonna
It'll
resolve.
become that.
Yeah.
Oh, okay, okay. So it's a, it'll never, it won't produce pure COCO2 because it's in equilibrium. So there will always be like COCO, there will always be this and there will always be that, you know, because it's in equilibrium. And it won't remain pure because if they do obtain pure, it'll just become that. And that's why. It'll just turn into
Oh, can I see like a few photos of the book? Just to like do, cause I like going on my book. You know what I'm saying?
This is one of my, this is like the only song by Weezer that I, yeah, that I have listened to, and actually like listened to more than once.
That make sense to everybody there?
Yeah.
Okay, we're gonna 5, 6, 7, 8, 9, 15. No, I think it's because since they're in equilibrium. They're in equilibrium, like that's what we did for R&D. It's about equilibrium and shit.
Because both of them are gas.
Huh?
Because both.
Yeah, both are gas.
But we have to probably like some.
Should all be here, 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14,
What is it?
17. We are all
Are none
here.
of these filtered? Are you sure? Oh yeah, because this is has the, this is the energy star. Okay. I swear I thought we did something. Here, let me check.
I have this. You want to do it?
Oh yeah.
What that's not. What, you don't, I don't know what this one is.
Well, look.
Because they're both gas.
Yeah, they're both a gas.
And this one is. Three.
Yeah.
And this one's three.
Because there's two. Yeah, there's two. Because there's one here and one here, and there's two there.
That makes sense.
Yeah, but the thing is, in the case in here, on the type thing, it is there's only one here, and there's two here. That's why I think that wouldn't the arrow point to them flat. You know? Yeah. It's confusing.
Wait, what part are you?
We're still looking at 5.
5 what?
5, 5, 5.
On page 40.
On page 4. Or page 39.
Oh, fuck. I just want to check this out. I didn't even see file.
Oh, yeah.
I wasn't. Fuck.
Just look at it right now. It's the one that we were talking about before. But it's the one that's like,
Bro, why can't I do this?
that way, but it's not. Oh, then maybe entropy goes that way, but enthalpy goes the other. That's why. Yeah, because we don't actually know. Or wait, do we know?
No. Because there's no change.
So we just have to assume that it gives us. Okay, that's
All
right.
reminded from
Yeah.
they go back and forth, but then the part with the molecules, they never be like both. You know how like we talked about like the arrows, and whatever those are arrows doing if it's here, they're not gonna be the same arrow, right? It's gonna pass around.
Yeah.
So therefore that's why it's not gonna be the same.
That is.
Sounds good.
Yeah.
So it's like the molecules, like you talked about how the arrows get like shot across the wall.
Yeah.
And they're never gonna be the exact same arrow because they already shot it out to the other side. So therefore it's gonna be like a back and forth direction.
Yes, they're just gonna use each other's ammunition.
Okay, yeah, let's go with the arrow then.
6.
Yeah, exactly.
Okay, that means that it's an equal. K forward is 0.5.
I'm gonna ask you to stop at 11:10. So any you have to do now until then. I've updated the sheet so you know where PLD stops.
It's end of the A to B.
We'll start that one. What are all these?
You forgot.
Because the K forward is big,
Still don't know.
and then the K reverse is little, which means it has to start higher up to do that little bump. You understand? Like if you were to like draw it in your mind, the ball results are
G. I literally said D, bitch. I literally. Where? I don't know. I just remember. My turn.
But they have a different direction. They have a different direction. They have a
Yeah, there's a minute. If there's a maximum, like you can, it's possible.
Did you find it?
But that isn't. That isn't.
No, sorry.
Yeah.
Energy is part of the This is the energy.
Really?
This is the amount.
I didn't see the folder in the.
Did you go through all of these?
Yeah, I did.
I got some more.
What is it now? Okay, graph is kind of
I thought it was blue.
And
Yeah. A
here.
versus time.
I thought you said you would bring it back to house.
A goes towards this and this.
And
Oh.
it's like
This is what you're.
Maybe I put-
This is the X value.
maybe in my,
minute. No.
So,
Then I brought them all back.
Because gas takes over
so
everything.
these are like the
Maybe I put it in, maybe it's in a folder I have somewhere, cause I was gonna bring it back to show you.
Yeah.
And then I didn't put it back in there.
Equilibrium time was at
Yeah.
9 minutes.
You're right.
Because it stays like this. It's not like dynamic, it keeps going back and forth. Or maybe it does, but not noticeable enough.
That is
or even a
science and ethics,
Because there's still.
so not you.
I guess it, yeah, maybe it is at 8. Yeah, because the rates are the same.
That should be.
Could be.
I think we look at the rates.
That table.
Yeah.
Yeah. Yeah, so it's at 8. What else occurs at equilibrium? And then the polarities, like the concentration, like they stop changing. Yeah. Okay, let's look at the answer though. Let's go back. See what this thing says. I got it right here. now let's go back to C. There's more questions here. I just wanted to look at.
Is it equilibrium?
Because you do need the masses have to, the molecules have to be the same too. The reactant products are constant, which means that they have to. Is there,
Like, it's gas.
okay, same is the time when these two are equal, so there is that.
Okay,
Sure. It's also on
They're
the
equal,
Google Doc.
Yeah,
but
it's
that's
two
not
pages.
equilibrium.
Is there? Which page? Can you email me the pages? Because I'll take pictures and
Yeah,
fix
the
it if
great search.
necessary.
It's
And then one is the
24
forward
and
rate, which
25.
is-
Okay, if you email me that, I will fix that in the future.
Which one?
For the forward rate, this is the forward rate is A. This is the A rate. This is the B rate. So the A rate is the greatest
Yeah.
one is that 0 because the more concentration, the more the quicker the rate, and then it becomes slower as there's less. Yeah. And then what is the numerical value of the ratio of product to
Nicholas
the
Meyer.
reactant at equilibrium?
It was in the bottom of these.
1/0.2.
I did bring it, but then I brought it back, but I brought it back with
Oh, this one is-
I sent it in email.
Okay, perfect. I'll fix it today.
Okay, let's actually see that one. Let's see.
Or as soon as I see the email.
Okay, so
Oh,
after
still got 2 more minutes.
However, even in reactions, the equation shows that one molecule that is
tell me.
does not require any
You're telling me.
that the reactant is part of the
Because I usually would
although it is
find out.
remotely possible.
You said that it's not.
It's just that.
Yeah,
It's kind of levels.
yeah, it is not true. We said that it's not true that they're at equilibrium. And forward rate is greatest when
That was
A
a
is
camera.
greatest, and this A decreases.
What do you guys do back?
And
This.
then the ratio is 1/0.2. Boom,
I
there we go,
mean, I
all
know,
of
but
them.
I was scrolling down and I saw this gigantic E and it just made me laugh. It's just so random.
What is the giant
This-
Eve?
No, no, this is like
feminized ally.
It's when A
Oh,
is
I-
greatest.
oh. Clever.
Yeah. It's the same thing.
Yeah.
Okay.
No can be
Yeah, 6 and 7 is when you're
Right.
shit.
So that's my correction. This way?
What have you done?
Well, that's the one that's what's on my page.
This is, I like that.
Right. Oh, I thought you said there was no chemical, like that was
No.
chemical evidence. There was, but I think people grabbed it.
Oh,
This
so
one
you
goes-
like
this one goes down, this one goes up.
But you could like
Well, I
They got
feel like
sit next to Nick, but I'm gonna stop.
it's-
Oh, it's been Sarah, stop me now
They
anyway.
just add more and it goes.
Okay, Becky, you need to put everything away.
That was 11.
Close your computers, put away your headphones.
no.
That's writing.
It's like a different kind
We're gonna describe a few things under Le Chatelier's principle and describe the term shift. Samuel, Andrew, pull out your notes, put away your laptops, the ones that were just handed out. We'll define shift first.
Is it not coming?
No, I think, didn't it say that you're learning about things? Yeah. Yeah, no, I'm just saying, bro, it shouldn't be, we can still probably switch. Like, I talked to Rodriguez and I'm like, is it possible to do a switch? Like,
A shift is a system's response to stress to reestablish equilibrium. As soon as you add something to the system, we're no longer at equilibrium. In the example I had where everybody's walking around desks, if I all of a sudden shoved a bunch of different people there, you'd have to start walking a lot faster. Put a lot of people on one side, they'd bunch up, they'd all have you move to the other side, and eventually reestablish equilibrium. The kind of things I'll do is I'll say like, oh, this amount goes up. And because it goes up on this side, then the equilibrium shifts that way. Or we increase the bromide and we shifted it that way. In my mind, way back when I was doing this in university or high school, one of the things I thought about that helped me really remember this is if this goes up, then it's literally doing that way and everything just slides down to the other side. And so it's a little sort of mnemonic. I find that helps to visualize a little bit. Also explains, in terms of visualizations, there's other ways that we could move this equilibrium without having to add any of these. Instead of adding some, I could take some away. If I added, say I threw in some lead nitrate, let's make it, +3 I think would be the best one. I might be wrong about that. None of those appear in the solution. Nitrate's not on either side. Lead's not on either side. The equilibrium will not change. But you will notice that if you add lead nitrate to it, if it was green, it becomes blue. It shifts it that way. What is something that the lead or the nitrate could be doing? So those are what we have in solution. What kind of things could they mess around with? Next, put away the. Where are you writing notes? Yeah, put away laptop. What does adding a metal ion possibly do to the other things in solution? Blowing it up, I don't think would. Did you say bomb or bond?
Bond.
Oh, bond is better. I thought you said bomb. I'm like, I don't really know how I'm going to work that one into. Yeah, it can make bonds. It makes bonds with bromide in particular, and you would get PbBr3. And so you would decrease the amount of bromide. If you decrease the amount of bromide, this concentration goes down. What's going to happen to this forward rate? It's going to decrease. And so this forward rate's going to decrease. Then this rate is all of a sudden faster than it, and that it gets more blue, and it goes faster, gives it more ammo until, again, the rates are equal. So they don't just have to go up, they also can go down, and that will cause the equilibrium to reestablish. So I'll draw those with like arrows and then arrows. Someone say this. Oh,
Where did the lead come
I just added it. Like a mystical being, I just went. I don't actually have that to do it with. The other ones are a lot safer. I prefer not to make lead compounds if I
from?
can.
So we can just put the leads in it?
Yeah. I mean, you're a chemist. You can do what you want.
I just don't know. How do you know which one best?
You'll know which one is best to do that if you wanted to do that once we do the solubility unit. And then we're actually going to do all of that.
So we don't need to know all of those.
You should know that if the concentration goes down, which way it's going to shift. You shouldn't have to, you don't know yet, I should add lead. You wouldn't know that. And this is just the first introductory page, So apply Le Chatelier's principle to a shifting equilibrium involving the following: a temperature change, a concentration change, and a volume change of a gaseous system. And the very next one we're going to do is we're going to look at some like very specific rates. So it should go. Yeah. This got moved on to the bottom thing. What kind of system would we have a equilibrium? Closed. If a closed system in equilibrium is subjected to a change, process will occur that tend to counteract that change. This is a negative feedback system, if you're familiar with that. A negative feedback system is a system, I don't think I spelled counter right. It says counter. A negative feedback system is if you try and make a change, it will immediately try to reverse it. One of the parts of engineering is trying to build negative feedback systems into your system. I think it was James Watt who did work on the steam engine, hence we use his name as a unit of power. He invented a system by which he had flywheels that were turning as the steam came out. If the steam was coming out too fast, the flywheels would start turning really quickly. And because they were turning, they were moving a valve. And if they went up, then the valve would close more, less steam would go out, and it would actually slow it down. And so that is how we used to feed the system oxygen. And so that if it was getting too hot, it would automatically slow it down and cool it. If it was getting cool, it would drop down, more oxygen would get in, and then the whole system could go faster. It's a negative feedback loop. So that way it stayed steady. Equilibrium in chemistry is a natural negative feedback system. If we increase one side, it'll shift to the other side and try and use it up. This is not the definition, but this is how I almost always define it, because this is what happens. Whatever we do, nature tries to undo. We have a lot of built-in negative feedback loops, particularly in our environment. We have natural ones in which there is natural, say, calcium carbonate deposits. We get a little bit of acid rain. They actually react with that and they undo that particular change. If it goes the other way, the calcium redeposits. And so it goes back and forth, keeping the pH of a variety of different lakes and our oceans in check. What we're worried about now is if we do too much, you can actually overwhelm the equilibrium. And if the equilibrium collapses, then lots of other things collapse. Equilibriums can only take so much. And so when scientists are talking about climate change and they're talking about this might happen, that might happen, oftentimes there's an equilibrium going on that's been existing for a very long time, and they're worried that that particular one is going to collapse. Any addition, kind of things. An addition is defined as a stress to the system. And when the system works, we talk about the system shifting. To offset that stress. I swear, when I originally had this, it wasn't like that. Is yours like that, where it was down a page? A line where it shouldn't be? No? So something happened putting it to there. So, we're going to start graphing some of these in terms of rate. That should probably help a little bit. We have a temperature change. And from last day, think of heat as just one of the reactants. You can increase it, you can decrease it, and it will shift to either add heat or remove heat. So if you increase the temperature, what color we should go with that? If you increase the temperature, you are adding heat. What is going on here? This is not the same, but put an approximate sign there. It is similar to adding just more AB. You're going to get a kind of similar graph. That stress is on the product side. And the stress on the product side is that we have too much, so which way is it going to shift? To the reactants, left. Do start getting used to saying reactants as well, because that's how we're going to define most things. So below this, I want you to draw a graph. Let's make T1 occur there. Let's make it green to fit the rest of them. Assuming that the concentrations start in each of these spots, theoretically they could start anywhere, but arbitrarily I'm going to say they start here, they go to this point, and then how does it shift? What kind of curve would you get? Where would be the most rapid change? At the beginning of the change or at the end of the change? Beginning. So you should draw it so there's a rapid change right away. Because you just added a ton of heat if you change the temperature very quickly, and then it would shift quickly, and then you would see it eventually peel off, and then you'd get a new equilibrium. When you got a new equilibrium, what kind of lines should you see? A straight line. Okay. Draw them. I'll come around and take a look at your guesses. Guesses? Yep.
When you A and B have the same concentration as one A.
Not necessarily. An equilibrium can have any amount of concentrations. They react in A plus B, but the amount that's in there.
So the amount is
A could be in huge excess. Equilibriums have that all the time. So just because a reaction is in a certain ratio doesn't mean that the amount of the system is in that ratio.
So B would drop faster than A.
B, why would it drop faster than A?
If you have 10B and 1000 A.
But they're not reacting in that ratio. They will drop at the same amount because it is A plus B.
Yeah, but it's concentration, right? So if you have 10A and 10B and 1000 A, and you take 10 of each and make them react with each other,
Yeah.
the concentration of B is 0, but the concentration of A is 700.
Well, we don't know the scale there, and the scale's the same for both. So if they both drop like by 2 moles, moles per liter, you'll see the same downward change. Does that make sense?
I guess,
Because
yeah, no,
it's not 10,000 to 1, it's like 3 to 2 or something like that. Yep.
So when you say shift,
Mm-hmm.
say if the concentration goes up on this one, does this side drop
No, if that side goes up, which way is it shifting?
to the left side?
You said that one went up.
Yeah.
So like added something to make it go up. So how will we get rid of it?
You have to balance it out on this.
No, you have to shift it to the other side.
What are you shifting to the other side?
The reaction will shift. So if you, what happens to the rate when you increase the concentration?
Hell no.
It increases.
It increases. So if the rate increases,
No.
what rate is increasing? The forward rate or the reverse rate?
Reverse.
So this rate's going like crazy. What's happening to that amount now that it went up?
Look at it right now.
It goes down.
So it
Yes,
balances
bro.
out when it goes this.
Yeah, so on this side, when the forward rate increased, you got more of that.
So you get more, so you start off with loss of concentration here, and
Yeah.
then the forward rate increases,
Yeah.
but that slowly decreases,
Yeah.
and then it fires back this way, right?
Yeah, and so this rate will go up and then remain steady.
And then
No,
it's,
no, right, this concentration will go up and then remain steady.
and then it's two equal.
Yeah, and then when it's equilibrium, it'll be straight lines.
Oh, okay.
We're gonna do that example, when I can increase the concentration, we'll show the graphs as well.
So this is right?
Yeah.
Wait, actually, I will go.
A will go down, yeah, it's looking good. Guesses, guesses, guesses.
I have no
You know if they're gonna go up or down?
I don't know.
You do.
I thought it
do.
becomes equilibrium. Like I thought they all become like
Okay,
together.
hold it.
Wait,
Where is it?
do you see these similarities? I don't.
No, don't erase that. That's a work of art. No,
Why?
because you make them all the same.
I know.
That's hilarious. This is like chemistry humor. They don't have to end up in the same spot. The only thing that matters is it going up or down? Give me a guess?
Oh, okay, yeah. That was,
No, Sam took my pencil.
Oh.
Okay.
How we do over here?
Is this right?
Okay, we got ups and downs.
Oh, I got blue
Um,
too.
And
when are they? When is
what you have activation energy in yours.
Where the blue
So they're going
socks?
up and down. That
Oh,
won't
but
happen.
they shouldn't. So
They should either go up and steady or down. Yeah, they won't go up and down. Those are good.
The glance back.
Those are good.
That's not.
Are you gonna wear that for United States?
Those are good. They're probably too straight. So we're gonna show you how to curve them, but it's a good guess. No, I think it is. No, I think you're good. Okay. Actually, it might be backwards.
Mine's the opposite.
Okay. Now we'll see.
I guess.
Was your guess okay? We added heat.
Okay.
Okay? Which way is it going to shift? It's good. So this side goes up. Can I do it? It's going to go up. So that means it's going to slide this way. What will happen to the concentration of A? If the rate increases this way,
Yeah.
this will increase. What will happen to B?
It will increase.
It'll increase. What will happen to the amount of A, B?
It'll decrease.
It'll decrease because it's being used up. So A and B have to go up, and they go up the fastest at the beginning. So you get a curve that looks like some of you just did it like that, which is fine. In that you're showing that it went up. That part's right. But to show that it goes up fastest at the beginning, you have to start out with a sharper curve, and then it equilibriums out, and then you get a straight line.
But what if you drew it in the reverse direction?
Then you shifted it in the wrong direction.
So you said mine's right.
The curve was right. I wanted to give you praise. Do you remember Mr. Felix? He's probably before your time.
No, I don't.
He had Mr. Sullivan's job before Mr. Sullivan, and he was actually at one point the house captain of Privet House, like ages and eons ago. Another teacher, Mr. Garvey, Mr. Felix was talking about how he was commended, and he was like, nobody was ever commended in Privet House at that time. What are you talking about? Mr. Felix was like, no, I really was. Like, I worked really hard. They're like, oh, right, I remember that. We told you were commended to make you feel better, but you really weren't. Mr. Sullivan, it was Mr. Felix, deputy head of school, absolutely crushed.
So now I see what it is.
So, similar time there, Gleb. I just wanted you to feel good. Okay, Kurt, is everybody okay with the types of curves? Is everybody okay with which direction now they went? We're gonna do it again. Notice there's no sharpness. Nothing just increased radically, and that's because temperature's not on this graph. The thing we increased was temperature. So you don't see that in the concentrations, but when we add something specific, we'll have to add it in. Also, this amount, whatever that is, like, say that is, whatever it is, that's 2. These two should be equal to each other. I know I didn't draw it very well there. But it's a 1-to-1 ratio, so their amount of shifting will also be 1-to-1. Where they are in the graph doesn't matter, because you can have an equilibrium at any point, but their shifting should be in the ratio of their balancing, because they can only react that way.
So if they apply heat in the reactant side,
Hold it. That statement creates the assumption that you can only add heat to sides. You can't add a heat to the product side and not the heat is being applied to the whole system.
Right.
The reaction has heat as a product, so the heat affects what will happen to the rate of both reactions when you increase the temperature. What happens to rate when you increase the temperature? It goes up. So the rates of both have gone up. But because this is a product, it has affected one side more than the other side. And that's your next graph. I would like you to graph the forward and reverse reaction rates. So let's see colors. I am going to make forward rate let's make it blue, and I'll make reverse rate red. What does blue and red make? Oh, excellent. So I have a color for that. So when they're together. So when we start out, if it's at equilibrium, if I do the same thing and I have time T1, we're not measuring concentration anymore. What should the rates be at equilibrium? They should be equal. So this first, both rates are the same, right until time T1. Now, I've added temperature. Both rates will increase. But which side has the energy term? This side. So which rate is affected the most? The reverse rate or the forward rate? This looks like, this is an endothermic. Hold it, endothermic? Exothermic. So this looks like this. And so we've added heat. So this has the most energy to overcome. We've got a lot. So we add energy, this rate gets affected the most. And so this reverse rate pops up the highest. So although they both go up, I need the other color, the reverse rate goes up more.
Wait, why would it go up more if it has more energy? Oh, not like when it goes down.
If you give $1,000 to someone who's living paycheck to paycheck, it has a higher impact on their life than someone who has $1 million. The reverse rate needs energy. That's what's limiting it. If you give it a bit of energy, its rate just increases faster because it's what it was deprived of. Probably the other rate was just based on them going back and forth. So that one increases the most. And so now it's going faster. So it's quickly throwing it to the other side. When it quickly throws it to the other side, what's going to happen to that rate as it starts to disappear? It's going to decrease. So this rate's going to start to go down. It's going to go down the fastest at the beginning. Now the forward rate is now getting extra stuff from the reverse rate. It's throwing over ammo. What's the forward rate going to start to do? Increase. So you get an increase going here with the forward rate, and then you get a decrease with the reverse rate, and they eventually meet in the middle. And then you have an equilibrium again.
What's purple?
Red plus blue.
I know, but like, what does it signify?
That forward, oh, okay. I'm just trying to indicate, because I can't if I try and overlap colors, the blue would just overlap the red. I'm trying to indicate that they're exactly the same. If it's at equilibrium, because purple, it's not purple, blue plus red is supposed to make purple. People in here said that and I believed them. I could be wrong. I failed that section of kindergarten. So a rate graph looks a little different. We see the spiking of rates because temperature will spike the rate right away. They both go up, but it affects the one that needs the energy the most. Now, in working it out, if that's difficult to think about, just treat it like a reaction. Oh, here's heat. I've added more heat. It goes that way. The reverse rate spikes the most, and the forward rate spikes the least. And then you just have to join them together afterwards. So that is a temperature graph. Oh, I didn't, there's some words up here I didn't fill. Reverse rate. Spikes. Highest. Then decreases. Spikes. Then decreases. Good. So for the next one, exactly the same reaction. Let's do that again. But now I want to see your drawings. Now that you've seen it once and you have your old one to refer to. Let's decrease the temperature. If we are decreasing the temperature, what are we doing to the heat on the product side? Removing it. So the stress is in the product, same as before, but now we're removing. And if we are removing heat, which way is it going to shift? To the right. So remove heat shifts to the right, to the product side. Also, looking at both of these, we added heat. By shifting to the left, the system removes heat. When we take away heat, by shifting to the right, it's going to add more heat. It's not a chemical process, but this is how water evaporation and freezing works. It's an exo and endothermic reaction. When water tries to freeze, it releases heat. And when you try and heat it up and evaporate it, it sucks in heat. Those are the similar processes, which is why here on the coast everything's so mild, because there's a natural feedback system there to regulate the temperature. So do the reaction rate here. So there, and here do the concentrations. I said the balancing was important, so I'm going to change it. I want to see them, let's make this B2. So we have no, that'll just be the same. What am I doing? Let's do that. Change the reaction very slightly. And then I can see how your concentration shifts. Reaction rate is on the right. I'll put a T1 there.
Huh? This?
And again, if you would decrease the temperature, what's going to happen to both rates? Decrease. Which one's going to be affected the most? Which one's going to be slowed the most? Because which side needs the heat? The products. And so they're trying to react that way. Can they if you take away all this money? No. So its rate is going to be slowed the most. The same side's being affected. It was increased the most before. Now it's decreased the most.
So the products would be decreased the most?
Pardon?
The products?
So the forward rate is going to decrease the most, which means you're going to get, that explains the shift. It's going to shift to the right the most because it's decreased the most. Similar analogy, if you're speeding down the highway and you get a $400 fine, and you're living paycheck to paycheck, that's going to affect you the most. Whereas if you have millions of dollars, that's just a fee for speeding down the highway. Draw your graphs and come around and take a look. What do you got? Yeah. That was it.
One of those times where you just leave.
Nope, no. Well, your color coding. Which one should go down the most?
The reverse,
Why?
because it's losing heat, so that's where everything happens.
And now your concentration graphs.
Oh, I didn't do that.
Yeah. Look at the other one. It's a very similar process. Yes. Make a longer initial part because it make it a little easier to read. But you can go there.
So now
It'll be
it's
sharp
right.
down. Like it sort of drops. I don't know if that's a deliberate thing. And also, I don't draw it properly.
There's no numbers.
But when you draw it going down,
They're on my finger.
because it starts off quick, that's a sharp drop off.
Oh, I didn't like.
Not a, because that implies slowly increasing.
Okay.
But that's just a quibble. Overall, it looks good.
You draw this. Is this right?
Huh?
That's looking good, yeah. Yeah. Nice graph. Now the concentration. Do you have different ratios for A to B by how much they go down?
No, it's all the same length.
Ah.
I just put length one, length two.
But it shouldn't be the same length.
It shouldn't for A.
I changed the example on you.
Oh, I didn't.
So here,
Oh, okay, then it would be 2 times.
yeah, so the B should go 2 times more than the other one.
Oh, B should be double.
Yeah, B should be double. I changed the example slightly. Just so that I can make that exact point.
Should be double. So A should be.
Luke, is this right?
Yeah, your rate one looks good. Those are looking good. And you've got the ratio there. Oh, are you packing up before the bell has gone?
Does that look good?
That is looking good. Is the B twice as much? It does look smaller. Are they intended to be the same or different from A? How much different?
Yeah, A.
2 times smaller.
There you go.
A decreases because if the heat decreases, then the reaction goes to the right.
More of a curve probably,
Like how?
because you're going like,
No, B decreases twice.
but it would actually start off quick and then taper out.
And then A decreases.
Thank you very much. You can probably start on this part of the Hampton now too once you get there. 2 to 1, 1 to 1. Yeah. Yeah. Now, but AB, what ratio is it to the other ones?
1-1.
1-1. So it shouldn't probably go up quite that high.
Oh, okay, yeah.
Yeah. You just got excited. Thank you, thank you.
Thank you.
Thank you.
Thank you.
And I will stop the recording.